All right. Hello, everyone. Welcome back. So we have a new lab today, and I already posted on Pivot Interactive. It's going to be through Pivot Interactive. So let me share that. Now that you have moved into Waves, it's easier for me to give you some Pivot Interactive labs. All right. So it's Lab 9. So we have standing waves. So I'm pretty sure that you already learned about standing waves and how to measure and find waves and things like that. So this is going to be then, you can write the learning objectives, apply the relationship between wavelength, frequency, and wave velocity using the standing waves, where the equation for the wavelength is, the velocity over the frequency. So we will be using this equation uh, to do our graphs, where the wavelength is inversely proportional to the frequency, and the velocity is going to be basically the proportionality, right? So that the slope. And then we're going to apply the relationship between wave speed, tension, and linear density for transverse waves in a string. So the second equation here is specifically only um, for the string. So this equation, right? So for this equation, this is only for the, string, because there's a mu, which is called, the linear mass density. This equals to mass of the string divided by the length of the string. That didn't work. Right, so the length of the string. All right, so using those equations, right, so we should be able to then get some of the information. All right, so let me very quickly uh, give you some of those equations in this whiteboard. All right, so think like this. So what you have here is, remember, standing waves means that you have your string trapped between two, let's say between two boundary points. And then if you start oscillating, you're going to generate a wave. And the wave is going to move like this and reach the boundary point, and then it's going to reflect back. But when it reflects, it changes orientation, right? So then it reflects like this. And then you get this shape, more or less. So I could have done probably better. So this, you get basically this shape. So this is known as a standing wave. Okay. So the standing wave has a string, right? So first of all, it's a transverse because it oscillates up and down relative to the direction of the wave motion. And one of the things we can do here is we can then relate, right? So wavelength to the velocity and frequency. And one of the things you will see here is you can relate the number of those standing segments that you see, because if you remember, right, so we have then 1, 2, 3, 4, 5, and 6. Those are known as nodes. So we write it like this with a capital N. And we also have 1, 2, 3, 4, 5. Those are known as antinodes. Right, so those are known as antinodes. All right, so generally then we use antinodes for this lowercase n, which is in a way sometimes known as a number of modes. So for example, if you have 1, 2, 3, 4, 5 antinodes, then your n is equals to 5. You have 4 antinodes, n equals 4, and things like that. Because the wavelength can also be related to the L, which is the length of the string between those two, boundary points, and the number of segments. So wavelength as a, function of, this mode number is equals to 2L over n. So for example, in this particular drawing that I have, since n is equals to 5, So then wavelength will have a length of, 2/5 times L. So if let's say if I have the length, right? If I have the length, then I can do that. For example, if the length is 1 meter, so I'm just basically 2/5 times 1 meter. So that's basically my length of one wave. And we will be then using this. We will be using some of those things where we can use this equation with combination of that equation to take a measurement of our experiment and find the velocity. So that means our experiment, from the experimental point of view, we're going to be, trying to find the velocity. And then we're going to be using velocity to find the linear density, which has this equation. So it's tension divided by mu. Tension divided by mu. And then since mu is equals to mass per length, then what we'll do here is we will then use this to get basically the mass. So mass is mass of the string. So that's going to be our goal. So our goal is mass of the string. All right, so I have a question. Isn't there 6 ends? Yes, the number of nodes are 6, but this is not number of nodes. This is mode number, which goes by the number of antinodes, and I have 5 of those, of the antinodes. So in this equation for the wavelength 2L over n, n is equivalent to number of antinodes, not number of nodes. Anyway, so this is basically mass of the string. Our goal will be to find mass of the string. Now, one thing I want to make it clear here is this. Okay, so our experiment involves so things like this. So this lowercase l is the entire length of the string. This is for the entire length of the string. But our experiment gonna have a setup where okay, so it's gonna have a setup where you have those boundary points. So basically our string gonna go like this, then gonna go over a pulley and gonna go down with some mass hanging. And we have in a way the L, right, which is this L over here, is the entire length. That means starting from point A, let's say that where the pulley here is, let's say point B, and then where the mass is attached, point C. So the length here is basically going from A to C. That's the entire length of the string. Okay, that's the entire length of the string. So in this equation for the mu, we are using that entire length of the string. Our experiment, however, going to be such that only the part from A to B of the string actually going to be oscillating. So only this part is going to be oscillating and giving us basically those, standing waves. Let's call that then, I don't know, L like this, uppercase L. So in a way, my wavelength equation will be 2 times that uppercase L. This L is known active length. So this is active L, basically. Active L, that means only the part of the entire length of the string that is oscillating. So B to C, see the length B to C is not part of it. So in a way, you can say that, the active length is only, so L is only equals to the length from B to C. Sorry, A to B. So it's AB length, where the entire length that we use in this equation. So that's basically sort of like boring, right? This L over here is AC, the entire length. But equation for the wavelength is actually only the active length, 2L over N. That means this is only like AB. Okay, so be careful in terms of the L when you are using in the equations of the wavelength and for the, let's say, linear mass density. To find the wavelength, using only active length. in the equation of the, linear mass density. Linear mass density is equals to mass divided by the entire length of the string. Are you guys okay with that? Any questions? All right, so let's go back to the lab. All right, so then this is what you can see, right? So here's our experiment where you have a string connected to the oscillator on the right end, and to the pulley, then down to the, basically to the attached mass on the left end. So one thing we're gonna do here is we're gonna see that the hanging weight is given to us. So let's say we have cord 1 and hanging weight, okay, 50 grams. So this hanging weight is then this, or the weighted set. This is actually hanging mass. So you have to understand, right? Hanging weight and hanging mass are different things. You're given 50 grams, that's the mass in grams. To find the weight, you have to convert this to kilograms, then times 9.8. Because in this equation, right, that I have for the, I don't like writing on this screen because it always freezes on me. Okay. See, for the velocity equals square root of force over mu, this force here is then equals to the hanging weight. That means equals to the hanging mass in kilograms times g, which is 9.8. Okay, so that means you have two things. This m here is the hanging mass. The m that we're trying to find, which is part of that equation, right, part of mu, is mass of the string divided by the entire length AC of the string. That means you're gonna use this equation. We're gonna find velocity from the graph, from the slope. We're gonna find the force from hanging weight, and then use that to calculate the mu. Once you have the mu, then you can rearrange, measure the entire length of the string, then solve for the mass of the string. Okay, so it's kind of, several steps that you have to do. All right, so let's go back. So you have some tools. For example, you can use this to measure, this vertical portion of the string, and this is to measure the horizontal. So then you add those two together. So you can say, right, this is roughly 100 centimeters. And this one is maybe another kind of like 15 centimeters or so. So overall 115 centimeters, but only 100 centimeters is going to be then oscillating when we, start the experiment. Now the experiment goes like this. So the string connected to an oscillator. So right now what you see here is you see there's basically no, oscillator is off. So once we turn on the oscillator, frequency increases, and as frequency increases, then you start, generating standing waves. With increasing frequency, then you get more segments and wavelength changes. So you can see right now wavelength changes because you have more segments, and there's more. That means we have now n equals 3. Then we get n equals 4. Then let's see if we get n equals 5. There you go, n equals 5. And n equals 6. There you go. That means we can get all the way to n equals 6. So your experiment will be, select any combination of string and hanging weight. Okay. So that means, let's say see cord 1, 50 gram, or cord 1, 70 gram, or cord 2, 50, 70, 100, any combination, and so on and so forth. So choose one of them. So let's say right now I'm doing 1 and 50, just to give you some, demo. That means try not to use 1 and 50 because I'm using that to give you it as a demo. So let's say then here you're going to plot in terms of your wavelength. And this is in meters, right? I don't know. So we don't need a variable because I don't know how to use, how to do in Greek, right? So this will be then frequency. All right. And units, I remember, it's hertz or 1 per second, right? So technically better to do 1 per second. Okay. And well, I can do F here, but you know, I don't know. I can do wavelength here, so let's not have variable. Okay, so let's do this. So think like this: when this was 0, this was 0. That means when frequency was 0, you know, the wavelength is 0. Then what I can do here, so I start my video and I stop when I see the maximum amplitude with the 1 segment. All right, so I think 1 segment has passed. So I go back and I think this is the maximum amplitude. So then I can see, right, it's more or less about 10.5 hertz. So I come back and say, all right, so 10.5. Then I need to find the wavelength. All right, so how do I find the wavelength? Well, according to that equation, wavelength equals 2 times L divided by N. Well, I measured, this is, the length here is 1 meter, and N is 1. Remember, so this is N is 1. That means lambda is equals to 2 times L over 1, and L is 1 meter, so 2 times 1 meter, so 2 meters. That means this is basically 2 meters. All right. So again, using this equation where lambda equals 2L over N, L is 1 meter, N is 1, we get 2 meters for that. Because here you can see, right, in 1 meter length, active length, you're only seeing half of the wave. So that's why the wave actually will be 2 meter long, because we're only seeing half of the wave. Then we go and see what will, you know, when will we get like maximum amplitude for the 2 waves? I mean, 2 segments, N equals 2. I think this is good enough. So I can go and say, all right, so this is roughly 20.5. Okay. And now my question is that what is wavelength? So who can tell me what is the wavelength? What is the length of one wave right now?
150 centimeters.
150? Why 150?
I think that was the length of the part that was oscillating. I don't know. I don't remember the exact number, but it's the length of the part that's oscillating.
Exactly. That's good. Well, no, it was only 1 meter. 1 meter, 15 centimeters. 1.15 is the entire length. So, but yes. So right now you can see, right? So you see basically entire wave, right? You see entire wave, which means that when you have N equals 2, you see the wave along the entire active length, which is 2L over 2 just gives you that wavelength equals length. That means this is basically 1 meter. And then we go and look at in terms of, okay, so when do we get 3? So you can see, right? So try to get like, let's say maximum amplitude. I think this is something like that. So I had 31.1. So I get 31.1. And then I look at, okay, so then what is wavelength? Well, the wavelength will be now 2L over 3, or 2/3 of L. Okay, so, or, you know, you can do something else. Now that you have, you know, all this length, you can take this, put it here, and measure the length of the wave. So who can tell me what do you measure for the one wavelength? What would you measure for one wavelength?
The antinode is?
What is it?
The antinode?
I can't hear you, sorry.
Are you counting the antinode?
No, I'm talking about, let's say if I need to find the wave, you know, the length of one wave, what value would you measure here?
Where the nodes are. So it would be like 32, 33.
No. So
is this 65?
Around 65, yes. So this is basically one wave. This is one wave.
Oh, gotcha.
And you basically measure somewhere over here. So roughly 65, yes. So then you can go and put here as 0.65, right? Because we're doing in meters. And then you can see, right? Then after that, you just basically do the same thing. So you go and, you needed to maybe calculate for the first one, but for the other ones, you don't really need to do anything. So after that, let's look at, okay, so when you have 4, right, so then you just basically measure now for the 4, which will be, well, roughly about 48 centimeters or something like that. And let's say wavelength is 41.5. So 41.5. And this is, I think, it was roughly 48. Anyway, so as you can see that this is basically how you do your measurements, more or less. And you need to do up to 6, measurements, right? So I did 5, you need to do up to 6. Or I need to up to, like, let's say, up to n equals 6. But this is for me good enough, because then I'm going to plot wavelength versus velocity versus frequency. Okay. And then I get something like this. I get something like that, which is means that I got something wrong. Yeah, because this is 0.48. Okay. There you go. I get something like this, which means my graph is not, linear. So I need to linearize this. To do that, we can see that in the equation, wavelength is proportional to 1 over frequency, because we have using this equation. So if I'm using that equation, then it means I had to plot wavelength with respect to 1 over frequency. All right. So then, that means I need to add another column to the right, and let's say 1 over the frequency. So units then will be seconds, because 1 over frequency, 1 over 1 seconds, right? You get this. So then you can do the equation for here as 1 divided by frequency, and automatically will give you that. Oh. So then if I go and over here do plot as a 1 over frequency, you can see right now I have more or less linearized. So curve, proportional, I get that. Now, what's the point of this graph? Well, the point is to get velocity. What is the velocity? Who can read the velocity value for me?
20.8 meters per second.
Exactly. That's the slope of this line, right? 20.8 meter per second. Now that you have the velocity and you have the hanging weight, then just go ahead and calculate the linear density. And if you have then linear density and the entire length of the string, then you can go ahead and calculate the mass of the string. And that's what you do for this, next few parts. Then you're going to do 2 more experiments. That means you're going to do a total of 3 experiments with 3 different, hanging weight and chord combination, and pretty much doing the same thing. That means I need to have mass of 3 different strings. And you can do like any combination, because as you could see, right, there's a chord 1 with several mass, chord 2 with several mass, chord 3 with several mass. So anything but do not do 1 and 50, because I use that for the demo. Any other combination will work, but not 1 and 50. All right. All right. Any questions? All right. That's pretty much it for this, guys. So if you have any questions during the week, send me an email. Otherwise, have a good one. I will see you all next Wednesday. All right. Take care.
Thank you, Professor.
You're welcome. Bye-bye.